Good day, everyone, and those joining us on YouTube. We're excited to present our research titled Purify Unlearnable Examples via Rate-Constrained Variational Autoencoders. This work by Yufei Wang, Songsha Wenyang, Shijian Liu, Yapeng Tan, and Alex C. Kott tackles the intriguing issue of unlearnable examples that can disrupt machine learning models. Our defense strategy not only neutralizes these threats, but also serves as a benchmark for evaluating existing methods. Stay tuned for a deep dive into our findings and their implications. Begin a frame title key highlights, begin itemize, item our defense strategy, begin itemize, item we present a robust defense strategy against UEs, which can be used to neutralize harmful data in training sets. Item this strategy can also be used to counter attempts at preserving data privacy. End itemize, item benchmarking potential, begin itemize, item our method not only serves as a strong defense mechanism, but also has the potential to be a benchmark for evaluating existing attack methods. End itemize, item raising awareness, begin itemize, item we aim to increase awareness about the vulnerability of current data protection techniques that use UEs, encouraging further research into more reliable and trustworthy data protection techniques. End itemize, end frame. In this slide, we delve into the key highlights of our research. We've identified a problem. Unlearnable examples, or UEs, are a double-edged sword. On one hand, they are promising for data protection, especially for proprietary or sensitive information. On the other hand, they pose significant challenges to data exploiters, who may view them as potential threats to a company's commercial interests. Furthermore, our research has revealed a critical vulnerability in current data protection techniques that employ UEs. This vulnerability underscores the need for more reliable and trustworthy data protection methods. In the following slides, we will discuss our proposed solution to these issues. Begin a frame title key highlights, begin itemize, item key insights, begin itemize, item our research demonstrates that rate constrained VAEs naturally remove poisoning perturbations in UEs by constraining the KL divergence in the latent space. Item, we found that most UEs have a lower class conditional entropy and can be disentangled by class-wise embeddings and a decoder. Item, we've developed a two-stage purification framework that consistently defends against UEs, showing impressive results across various datasets and perturbation levels. Item, we've also explored partial poisoning scenarios and proposed a detection purification approach that achieves high accuracy in detecting unlearnable data. End itemize, end frame, On this slide, we delve into the key highlights of our research. Our main method introduces a purification framework that utilizes a rate-constrained variational autoencoder, or VAE, to effectively remove added perturbations from unlearnable examples. This framework, which we call D-VAE, is designed to generate a reconstructed image that has minimal poisoning perturbations. This is achieved by constraining the KL divergence in the latent space. Furthermore, D-VAE has the unique ability to disentangle predicted perturbations using a trainable class-wise embedding. This means that it can separate the perturbations from the original data, allowing us to better understand and mitigate their effects. In essence, our method provides a robust defense against poisoning attacks, while maintaining the quality of the reconstructed images. Moving on to the key highlights of our research. We've made several significant contributions. Firstly, we've developed a novel defense strategy against unlearnable examples, or UEs. This strategy is versatile and can be used in two ways. It can neutralize malicious data within a training set, ensuring the integrity of our models. Additionally, it can also thwart attempts at preserving data privacy, making it a powerful tool in the right hands. Secondly, we've introduced a new network, the D-VAE. This network is capable of disentangling added perturbations from the original data. It can then generate purified data, free from these perturbations. This is a significant step forward in dealing with UEs, and we're excited about the potential applications of this technology. In summary, our research presents a strong defense against UEs and introduces a powerful new tool in the form of the D-VAE. We believe these contributions will have a significant impact on the field. Begin a frame title key highlights, begin itemize, item we've delved into the related work, discussing the current state of research and how our study builds upon it. Item we've engaged in a thorough discussion, analyzing our findings and their implications. Our methodology has been detailed, providing a clear understanding of our research process and the steps we took to ensure accuracy and reliability. End frame. Let's delve deeper into the problem we're addressing. Machine learning models, as powerful as they are, have a vulnerability. They can be tricked by what we call unlearnable examples, or UEs. Now, what are these UEs? They are essentially malicious perturbations, introduced during the training phase of a model. These perturbations are subtle. They slightly modify correctly labeled training examples. The goal: to maximize the testing error, thereby undermining the model's performance. Now, take a look at the figure on the screen. This gives you an overview of the D-VAE and our proposed two-stage purification framework. The D-VAE consists of two components, which we'll be discussing in detail as we progress. This framework is our proposed solution to tackle the problem of UEs. Stay tuned as we unravel how this works. Let's delve into the heart of our solution. The D-VAE and our two-stage purification framework, as shown in the figure. Unlearnable examples, or UEs, pose a significant threat to machine learning models. They create discrepancies between the training and testing data distributions, which can severely impact the performance of these models across various tasks. Our proposed framework aims to address this issue. The D-VAE, a key component of our solution, helps in disentangling and removing poisoning perturbations from UEs. This process aids in bridging the gap between the training and testing data distributions, thereby enhancing the model's performance. We'll explore this in more detail in the following slides. Begin frame. Frame title: Our approach. Two-stage purification framework with D-VAE. Begin a figure. Centering: include graphics. Width equals 0.8 text width. Height equals 0.45 text height. SRC task underscore execution extracted underscore paper underscore data. 2405.01460v1. Figures. 2405.01460v1 figure 1:1.png. Captiona tinea. The D-VAE and the two-stage purification framework in action. End a figure. Begin itemize. Item our solution. We propose a two-stage purification framework using D-VAE. Begin itemize. Item stage 1. We recover and remove heavy perturbations by training D-VAE with a small KLD target, creating a new dataset. Item stage 2. We generate purified data by training D-VAE with a larger KLD target, resulting in a purified dataset. This approach allows us to reconstruct unlearnable examples using representations with limited capacity. End itemize. The result. Our experiments show that training D-VAE with just 1% UEs is adequate for generating additional UEs, demonstrating the effectiveness of our approach. End itemize. End a frame. Begin a frame. Frame title: Our proposed solution. The two-stage purification framework. Begin a figure. Centering: include graphics. Width equals 0.8 text width. Height equals 0.45 text height. SRC task underscore execution extracted underscore paper underscore data. 2405.01460v1. Figures. 2405.01460v1 figure 2:2.png. Captiona tinea. The two-stage purification process using D-VAE. Stage 1 recovers and removes heavy perturbations, while stage 2 generates purified data. End a figure. Begin itemize. Our approach. We propose a two-stage purification framework using D-VAE. This framework is designed to handle unlearnable examples, or UEs, which are a significant challenge in machine learning. Stage 1. The first stage recovers and removes heavy perturbations from the UEs. This is achieved by training the D-VAE with a small KLD target, which helps to minimize distortion. Stage 2. The second stage generates purified data by training the D-VAE with a larger KLD target. This stage further refines the data, resulting in a purified dataset. Results. Our method has shown remarkable performance across various datasets and perturbation levels, demonstrating its potential as a consistent defense against UEs. End itemize. End a frame. Begin a frame. Frame title: A two-stage purification framework. Begin a figure. Centering: include graphics. Width equals 0.8 text width. Height equals 0.45 text height. SRC task underscore execution extracted underscore paper underscore data. 2405.01460v1. Figures. 2405.01460v1 figure 2:2.png, captiona tinea, the two-stage purification process in action. End of figure. Begin itemize. Item stage 1. The D-VAE is trained to recover and remove heavy perturbations from the Unlearnable dataset. This results in a new dataset, P1. Item stage 2. The D-VAE is trained again, this time with a larger KLD target, to generate purified data. This results in the final purified dataset, P3. Item: the purification process is designed to handle varying perturbation levels and has shown impressive results across multiple datasets. End itemize. End of frame. On this slide, we delve into the key innovations of our research. We introduce the D-VAE, a novel network that has the ability to disentangle added perturbations and generate purified data. This is a significant step forward in dealing with unlearnable examples, or UEs. The second innovation is our unified purification framework. This framework is designed to counter various UEs, providing a consistent defense mechanism. As you can see in the figure, it provides an overview of the D-VAE and the two-stage purification framework. The D-VAE consists of two components, each playing a crucial role in the purification process. These innovations are the cornerstone of our research, and we believe they will significantly advance the field of machine learning security. Begin our frame. Frame title: our related works. Begin itemize. Item: expanding the scope of UEs. Begin itemize. Item: our disentanglement approach can increase the amount of UEs, even when the attacker has more clean data. This was demonstrated using the CIFAR-10 dataset. Item: training. A D-VAE with just 1% UEs can generate additional UEs, proving the effectiveness of our method. End itemize. Item: detecting and addressing partial poisoning. Begin itemize. Item: in real-world scenarios, only a fraction of the training data may be contaminated. We evaluated these scenarios by introducing UEs to a portion of the training data. Item: we discovered that even perturbations learned for clean samples can serve as poisoning attacks. This led to the creation of a new Unlearnable dataset, PO. Item: our detection method achieved high accuracy, with almost 100% recall rate, allowing us to detect the presence of unlearnable data. Item: to address partial poisoning, we proposed a detection purification approach, which showed promising results. End itemize. End itemize. End of frame. Begin our frame. Frame title: our related works. Begin itemize. Item: Liu et al. 2023, begin itemize. Item: this team delved into the realm of partial poisoning scenarios. They introduced unlearnable examples, or UEs, into a portion of the training data, simulating real-world contamination. Item: they also ventured into the use of defenses based on pre-processing and purification before training. This approach aimed to neutralize the impact of UEs on the model's performance. End itemize. End itemize. End of frame. Begin a frame. Frame title: our approach. Begin itemize. Item: unlearnable data detection. Begin itemize. Item: we create a new unlearnable dataset, PO, where each sample is formed as X0 plus P0. Item: models trained on P0 achieve high accuracy on unlearnable samples but perform poorly on clean ones. Item: this discrepancy serves as a metric to detect the presence of unlearnable data. End itemize. Item: purification framework. Begin itemize. Item: we propose a two-stage purification framework that consistently defends against UEs. Item: our method shows remarkable performance across various datasets and perturbation levels. End itemize. Item: future work. Begin itemize. Item: we plan to extend our work to purify UEs that target unsupervised learning scenarios. End itemize. End itemize. End of frame. Moving on to related works, we delve into the detection and purification approach. This method is particularly useful in addressing the issue of partial poisoning in datasets. It involves a two-step process. First, we detect the presence of unlearnable data. Then, we purify the dataset to remove these unlearnable elements. However, it's important to note that this approach has its limitations. While it can achieve high prediction accuracy on unlearnable samples, it doesn't perform as well on clean ones. This is a key area for future research and improvement. In the next slide, we will visually demonstrate the effectiveness of the purification process. Stay tuned for some intriguing results. In this slide, we delve into the related works that have shaped our research. We've used the CIFAR10 dataset extensively in our experiments. This dataset is a collection of 60,000 32 by 32 color images in 10 classes, with 6,000 images per class. It's a commonly used dataset for image classification tasks and has been instrumental in evaluating the effectiveness of our proposed method. By using CIFAR10, we were able to test our model under controlled conditions and compare our results with previous studies. This has allowed us to validate our approach and ensure that it contributes positively to the field. Begin a frame. Frame title: Our approach. Two-stage purification framework. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. SRC task underscore execution extracted underscore paper underscore data. 2405.01460 V1. Figures. 2405.01460 V1 figure 1:1.png. Captiona Tinea, the two-stage purification process using D-VAE. End of figure. Begin itemize. Item. Our solution involves a two-stage purification framework using D-VAE. In the first stage, we recover and remove heavy perturbations from the Unlearnable dataset. This is achieved by training the D-VAE with a small KLD target. Item. In the second stage, we generate purified data by training the D-VAE with a larger KLD target. The result is a purified dataset that can be used for further analysis. Item. We also propose a learning approach that maps the summation of a trainable class, wise embedding, and the latents to perturbations through an auxiliary decoder. This helps us recover most of the ground truth perturbations. End itemize. End of frame. On this slide, we delve into the technical details of our proposed research. As you can see in the figure, we present a visual depiction of our D-VAE and the two-stage purification framework. D-VAE contains two components, which are integral to our approach. Now, let's talk about the problem we're addressing. Unlearnable examples, or UEs, are seen as a potential avenue for data protection against unauthorized use of proprietary or sensitive data. This is a significant issue in today's data-driven world. However, these methods pose challenges to data exploiters, who may view them as threats to commercial interests. Our research aims to navigate these challenges and explore the potential of UEs in a way that balances data protection and commercial interests. Stay tuned as we delve deeper into our methodology in the upcoming slides. On this slide, we delve into the technical details of our proposed solution. As you can see from the figure, our approach is based on a two-stage purification framework, which includes a component known as D-VAE. This framework is designed to combat unlearnable examples, or UEs, which are a significant challenge in data protection. Our defense strategy has two main objectives. Firstly, it aims to neutralize malicious data within a training set. This is crucial in ensuring the integrity of our models and the accuracy of their predictions. Secondly, our strategy is designed to thwart attempts at preserving data privacy. This might seem counterintuitive, but it's important to remember that data privacy can sometimes be used as a shield for malicious activities. In essence, our proposed solution is a powerful tool that can be used to safeguard our models and data, while also serving as a benchmark for evaluating existing attack methods. It's a step forward in making our data protection techniques more reliable and trustworthy. Begin a frame. Frame title: A two-stage purification framework and D-VAE. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. SRC task underscore execution extracted underscore paper underscore data. 2405.01460 V1. Figures. 2405.01460 V1 figure 1:1.png. Captiona Tinea, the two-stage purification process using D-VAE. Stage 1 recovers and removes heavy perturbations, while Stage 2 generates purified data. End of figure. Begin itemize. Item 2 stage purification framework. Begin itemize. Item stage 1. The D-VAE is trained to recover and remove heavy perturbations from the Unlearnable dataset. Item stage 2. The D-VAE is trained again, this time to generate purified data. End itemize. Item D-VAE. Begin itemize. The D-VAE is a unique approach that maps the summation of a trainable class-wise embedding and the latents to perturbations through an auxiliary decoder. The D-VAE is optimized using a loss function that includes distortion, recovery of perturbations, and a rate constraint. End itemize, end of frame, .. On this slide, we delve into the core of our research and its technical aspects. As you can see from the figure, it visually depicts our two-stage purification framework and the D-VAE, which consists of two components. Our research primarily revolves around two key questions. Firstly, we aim to understand the vulnerabilities in current data protection techniques that utilize unlearnable examples, or UEs. These UEs, while promising for data protection, can also pose significant challenges and threats. Secondly, we aspire to stimulate further research in this field. We believe that by understanding these vulnerabilities, we can pave the way for more reliable and trustworthy data protection techniques. In essence, our research is a call to action for the scientific community to address these vulnerabilities and work towards more robust data protection methods. On this slide, we delve deeper into the technical aspects of our research. As you can see in the figure, we have a visual representation of the D-VAE and the two-stage purification framework. The D-VAE is composed of two key components that work together to achieve our goal. Now, let's talk about our experiment design. We've evaluated partial poisoning scenarios by introducing unlearnable examples, or UEs, to a portion of the training data. This data is then combined with the remaining clean data. We've also created a new Unlearnable dataset, denoted as PO. This dataset is crucial in testing the effectiveness of our method. It's through this rigorous testing that we can ensure the robustness and reliability of our approach. In the next slides, we'll discuss the results of these experiments and what they mean for our research. Stay tuned. In this slide, we delve deeper into the technical aspects of our research. As you can see in the figure, our method employs a two-stage purification framework using D-VAE, which is a unique combination of detection and purification. This approach is specifically designed to tackle the issue of partial poisoning in datasets. Our D-VAE model consists of two main components, which work together to detect and remove unlearnable data. The performance of models trained on this purified data then serves as a metric to detect the presence of unlearnable data. This innovative approach allows us to not only identify but also rectify the issue of unlearnable data in our datasets, thereby improving the overall quality and reliability of our models. Remember, the goal here is to create a more robust and reliable dataset, free from the influence of unlearnable data. This is a crucial step in ensuring the accuracy and effectiveness of our machine learning models. Let's delve deeper into the technical details of our proposed research. As you can see in the figure, we have a visual depiction of the D-VAE and the two-stage purification framework. The D-VAE contains two key components. Firstly, we have the unlearnable dataset, denoted as P0, which we input into the D-VAE. We then use a two-stage purification process. In the first stage, we recover and remove heavy perturbations by training the D-VAE with a small KLD target. This results in a new dataset, P1. In the second stage, we generate purified data by training the D-VAE with a larger KLD target, creating another new dataset, P2. We then perform inference with the trained VAE on P2, saving a new dataset P3. This process allows us to largely reconstruct the data using representations with limited capacity. The overall network is optimized using an improved loss function, which balances distortion, recovery of perturbations, and a rate constraint. In our experiments, we found that training the D-VAE with just 1% of unlearnable examples was adequate for generating additional unlearnable examples. This demonstrates the potential of our approach for increasing the amounts of unlearnable examples in a dataset. Begin a frame. Frame title: a two-stage purification framework. Begin a figure, centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, src task _ execution extracted _ paper _ data, 2405.01460 v1, figures, 2405.01460 v1 figure 1:1.png, captiona, tinea, the two-stage purification process using D-VAE. Stage 1 recovers and removes heavy perturbations, while Stage 2 generates purified data. End of figure. Begin itemize. Item section 2. Purification of unlearnable examples, VAEs. Begin itemize. Item key result. The paper introduces a two-stage purification framework using D-VAE. In the first stage, heavy perturbations are recovered and removed. In the second stage, purified data is generated. This process results in a purified dataset P3. Item implication. This framework allows for the effective purification of VAEs, which can significantly improve the performance of models trained on the dataset. End itemize, end frame, .. Moving on to our technical results, let's delve into how we address partial poisoning. As you can see in the figure, our two-stage purification framework is illustrated, which is a key component of our D-VAE model. Now, partial poisoning is a scenario where only a fraction of the training data is contaminated with VAEs. In such cases, our method adopts a detection purification approach. The performance of models trained on this purified data shows significant improvement. What does this mean for us? Well, it indicates that our method can effectively reduce the impact of VAEs, even when they are present in only a part of the training data. This enhances the robustness of the models we train, making them more reliable and efficient. In essence, our method provides a consistent defense against VAEs, ensuring the integrity of our data and the accuracy of our models. Begin frame title. Increasing the amounts of VAEs. Begin itemize. Item. Our disentanglement approach can generate more VAEs from clean data. Begin itemize. Item. We experimented with the CIFAR10 dataset, generating VAEs from a small portion and leaving the rest untouched. Item. After training the D-VAE on these VAEs, we added them to the clean data, creating a new Unlearnable dataset. Item. Even with just 1% VAEs, we could generate additional VAEs effectively. End itemize, end frame, begin frame title. A partial poisoning and VAEs detection. Begin itemize. Item. We evaluated scenarios where only a fraction of the training data is contaminated with VAEs. Begin itemize. Item. We discovered that even perturbations learned for clean samples can serve as poisoning attacks. Item. This led to the creation of a new Unlearnable dataset, where models trained on it performed poorly on clean data. Item. This performance discrepancy can be used to detect the presence of Unlearnable data. Item. Our detection method achieved high accuracy, with almost 100% recall rate. Item. To address partial poisoning, we proposed a detection purification approach. End itemize, end frame, In conclusion, our proposed method stands as a benchmark for evaluating existing attack methods. It has the potential to significantly contribute to the field, and it underscores the need for further research to develop more reliable and trustworthy data protection techniques. In practical scenarios, our method has shown high detection accuracy. It remains effective even when only a fraction of the training data can be contaminated, demonstrating the robustness of our approach. In essence, our work is a call to action for the research community to address the vulnerability of current data protection techniques. We hope this will inspire new ideas and solutions to ensure the security and integrity of our data. Thank you. As we conclude, it's crucial to highlight the importance of raising awareness about the vulnerability of current data protection techniques. This is not just a theoretical concern, but a pressing issue that emphasizes the need for more robust and reliable data protection methods. Our work is a call to action for the research community. We need to stimulate further research in this area to ensure that our data protection techniques can withstand the challenges posed by Unlearnable examples. This is not just about defending against attacks, but also about preserving privacy and maintaining the integrity of our data. Let's work together to create a safer, more secure digital world.